Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is the principles, advantages and routing techniques of differential signals. In modern high-speed digital circuits, we often hear about an important concept, differential signals. Whether it's USB, HDMI, PCIe or high-speed DDR memory interfaces, differential signals are everywhere. Today, let's take a deep dive into how differential signals work, why they are so important, and the basic requirements for routing them. Just like in this circuit, there are many differential signals. If we zoom in, we can see that those labeled with a /n and /p, just like their names, represent a pair of differential signals. There are many differential signals present in this circuit. First, let's talk about the definition and working principle of differential signals. What is a differential signal? Unlike the single-ended signals we're familiar with, which use one signal line referenced to ground, a differential signal is transmitted using two wires, usually called a differential pair. These two wires carry signals that are equal in magnitude but opposite in phase. For example, if one wire carries +1 volt, the other wire will carry 1 volt. If one wire changes from +1 volt to 1 volt, then the other wire changes from 1 volt to +1 volt. The receiver identifies the signal by detecting the voltage difference between these two wires. With differential signals like these, the two transmitted signals have the same amplitude but are completely opposite in phase, so they serve as references for each other, and the receiver simply references these two signals. In contrast, the single-ended signals we used before, like these single-ended signals, have a fixed voltage value, and their reference point is GND. The working principle is that the receiver focuses on the potential difference between the two wires, rather than the absolute potential of each wire relative to ground. It's like two people starting from the same point at the same time. One takes a step east, the other a step west. No matter how the ground shifts, that is, no matter how external noise affects them, the relative distance between them is predictable, and the receiver measures exactly this relative change. What is the core advantage of differential signals? Differential signals are widely used in high-speed circuits, mainly thanks to two core advantages. First, powerful noise immunity, also known as common mode rejection. External electromagnetic interference and power supply noise usually form as common mode noise, simultaneously affecting both lines of the differential signal. Since the receiver only cares about the difference between the two signals, the noise components that are common to both lines are cancelled out when the differential signals are subtracted. This is like two people walking in sync. If the ground moves up or down together, the relative distance between them remains unchanged. This gives differential signals extremely high immunity to external noise. If we use the ground as a reference and the signal line is interfered with, its voltage may no longer change as expected, which could cause the receiver to detect an incorrect logic level. But differential signals do not have this problem. Both signal lines are interfered with simultaneously, so the difference between them remains unchanged. Second, they significantly reduce electromagnetic interference and radiation. The two wires in a differential pair carry currents of equal magnitude but opposite direction. The magnetic fields generated by these two currents are also opposite in space, so they cancel each other out, greatly reducing electromagnetic radiation to the outside. This means that using differential signals can help PCB designs more easily pass strict EMC certifications and reduce interference with other circuits or devices. In addition to these 2 points, differential signals can usually support lower voltage swings and higher transmission rates, which is why most high-speed signals are differential signals. Just like the USB 3.0 and HDMI we mentioned earlier, these all use differential signals for transmission, basic requirements for differential pair routing. Due to the special characteristics of differential signals, there are strict requirements for their routing on PCBs. First, the wires must be routed in pairs, and the two lines must always remain closely parallel to each other. Just like we see here with these differential signals, this is a pair and this is a pair. They always maintain a parallel state. The lengths must be kept consistent. The physical length of the two lines from start to finish must be as equal as possible. For example, this line has undergone some length matching adjustments. Since the outer line inevitably becomes longer when turning, it finds a suitable spot at the end and uses some serpentine routing to adjust the lengths to be consistent, maintain consistent spacing. The spacing between the two lines should also be kept as constant as possible. This spacing can be kept constant because during routing you can choose differential mode routing, and the software will ensure that the spacing between the two remains unchanged. Reference plane. Differential signals usually require a complete ground plane nearby as a reference, which means there will be some adjacent area next to it. However, if the differential signals are too densely packed, then the surface layer, or the top layer, cannot have ground copper pulled, but the bottom layer or inner layers can. Today we learned about the definition of differential signals, their strong resistance to interference, noise, and low radiation advantages, as well as the basic principles of routing. These characteristics make differential signals the cornerstone of high-speed, high-performance electronic design. In the next video, we will apply these theoretical concepts to practical operations, learning how to set up differential pair rules in the tool and mastering key matching techniques. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.